Hello, welcome back. In the last video we have seen how to see the convergence of Fourier series when the signal is piecewise smooth function. That means if the function is at finitely many points is discontinuous, but it is having a jump discontinuity, and other places it is a continuous function, it is actually differentiable function. So, in that case you can have the convergence of the Fourier series to the function at the continuous points. If it is at discontinuous points, you take the average value of a jump, that is half of the jump, average value of the jump of the function. That means function at both the ends you consider and take half of it, you sum of it and take the half of the sum. So, that is what you have seen, and there is sufficient conditions for the convergence of the Fourier series. In this video what we will have is when the signal is a piecewise continuous function, and a priori you know that if the Fourier series is converging uniformly, okay, we are asking more than piecewise more than convergence, pointwise convergence. That means if you assume that it is a uniform convergence of the series, the Fourier series that we have is uniformly converging to a function, to certain function, then that function must be the function f at continuous points. At other points where it is discontinuous, you have half of the jump. Okay, that means average value of the jump. That is what we will see here. So, it is not, the result is that not that significant, because we are not looking at the convergence of the Fourier series. Rather, if it converges, it has to converges to the function value or the average value of the jump, both sides of the function at the jump. Okay. So, we are actually assuming that it is Fourier series itself is converging. So, what we are still doing is in the process we can make use of a delta function that is useful when you are doing the Fourier transforms and Laplace transform later. So, you will understand what is a Fourier delta function and its use in the convergence of this series, Fourier series, when a priori you know that it is actually converging uniformly. Okay. So, we will write it as sufficient conditions. Before I do this, what is the convergence of uniform convergence? One sufficient condition is, so if you consider this as a Fourier series, Cn e power I n omega naught x. So, this is your Fourier series, okay, n is from minus infinity infinity. So, this is your Fourier series. So, if this converges uniformly means this sequence of partial sums, that is n is from minus k to k Cn e power I n omega naught x, this has your Sn. This sequence converges to the function which is finite. So, it is e power I n omega naught x. So, uniformly means irrespective of the value of x. So, you have the convergence is uniform. So, a pace of convergence is you have a minimum pace of convergence at all values that converges. So, you have a minimum pace of convergence that works for all values of x. That is crudely saying uniform convergence. Pointwise convergence means for different x values you have a different pace, and so when you consider some x values, so if you consider the limit of these x values, it may go to the minimum pace may not be positive. So, that may go to 0. Okay. So, that means it may not be convergence going with the same pace. Okay. There is no uniform pace at which this converges for all values of x. So, what are the sufficient conditions for this uniform convergence is if I assume that this coefficients, Fourier coefficients, n is from minus infinity infinity. If this is finite, I can say that this is uniformly convergent. Then this Sn converges uniformly. So, this is easy to see, because if you look at the Sn, modulus of Sn, this is less than or equal to sigma Cn, n is from minus k to k, okay, mod Cn. So, you can have this mod of Cn. Because of this, so Sn is a function of x. So, I can write it as a function of x. This is significant to this. So, this converges by M test. So, each of this is bounded with this, okay. So, and this is bounded with this, because this is series is finite as a number series, and this is from minus infinity to infinity. So, this is finite. So, once you have this, so you can easily see that this is by m test of convergence, Sn of x converges uniformly. Irrespective of x value, this is always converging. So, that is what you can easily see. Okay. So, Fn of x converges to Fx uniformly. So, this m test is, if you have Fn of x is bounded with some mn for each n, and mn converges to m, then you can say that Fn of x converges to, or rather sigma mn is finite. If sigma mn is finite, then Fn of x sigma Fn converges uniformly. So, that is a m test. So, I am using from calculus. So, if you use this, so you can see that if this is the sufficient conditions to ensure that this Fourier series is converging uniformly. So, I make use of this and to state this result. So, let me write a small theorem. So, if the signal f of x is piecewise smooth, not smooth. So, piecewise only continuous function, and sigma c n is from minus infinity to infinity. If this is finite, then the series, the Fourier series converges and is from minus infinity to infinity c n e power I n omega naught x is equal to f x if f is continuous at x. Otherwise, you will have to take the jump value. Okay. So, it's average of the jump. So, that is sum of the limiting values, take the half of it if f is having jump discontinuous. F is discontinuous. If at all it is discontinuous, it should be jump because it is a piecewise continuous function. Okay. So, if at all this if you assume that this is true, then you have this Fourier series converging uniformly. So, if it is a piecewise continuous function, or rather just continuous function, you cannot say that Fourier series need not converge. Okay. You cannot say that Fourier series converge. So, the Fourier series need not converge for a continuous function, that is in the literature. We will not look into those details. But why, when you choose certain piecewise continuous functions which we normally assume, if you just write it as elementary functions, and certain piece how you represent as a elementary function, another certain piece another certain piece you have a elementary function that is represented as a function, then these are because these are elementary functions, they are actually not just continuous, they are also differentiable. That is why it is actually piecewise a differentiable function or piecewise smooth function. That is why the Fourier series converging, that is what you are seeing in all these examples so far. Okay. And you will also see many examples, because by considering, when you consider a function with elementary functions, it is actually piecewise a smooth function. So, that your Fourier series converging actually to the function f or its average value of the jump. So, if it is a piecewise continuous function or a continuous function, the Fourier series need not converge. Okay. We have examples in the literature, but here if the Fourier series is converging, and it has to converge to the value of the, it cannot converge to some other thing except but it has to converge to the function f x if f is continuous at discontinuous points, it is the jump value, average jump value of the function at the discontinuous point. Okay. So, to show this, the result is, as I said earlier, this is not, result is not that significant. The proof, we make use of delta function, so that will be useful later. Okay. So, how do I see this? This is actually this series is converging to f x. So, let s of x, let me call this full series as s x, n is from minus infinity to infinity c n e power I n omega naught x. Okay. So, this you can represent as now we know because it is a Fourier series, and we know what is the c n. c n's are, where c n's are 1 by L minus L by 2 to L by 2 f x, these are the Fourier coefficients, minus I n omega naught x dx. So, if you substitute here, and you see that is going to be minus infinity infinity. Cn I substitute here these Fourier coefficients f x e power minus I n omega naught x dx times. So, let me put it as because I already have x, let me use this dummy variable t. So, this is t e power I n omega naught x. So, if we club together, so what you get is n is from minus infinity infinity 1 by L minus L by 2 to L by 2 f of t e power minus n omega naught or plus omega naught x minus t dt. So, here I split this, I take n equal to 0, I write separately. N equal to 0, if you take this is 1. So, you have 1 by L minus L by 2 to L by 2 average value of f of t plus. Now, if you write this as n is from minus infinity infinity, but n is not equal to 0, what is left here? So, that is minus L by 2 to L by 2 f of t e power min I n omega naught x minus t dt. So, this is equal to, if you actually combine negative and positive, okay. So, negative part if, so this is where I am using the uniform convergence, okay. So, uniform convergence, so this is what I am using. So, if this is true, this is a series is uniformly convergent. If it is uniform convergent, it's absolutely, it's actually uniformly and absolutely convergent. So, that means I can do the, I can shuffle all the terms and I can add n term to, for example, here a minus infinity term plus infinity term or minus k term plus k term, and so are all kinds of sum. You reshuffle, rearrange the terms and you can add it, you still converge to the same value. So, if I do that, I have 1 by L minus L by 2 to L by 2 f of t dt plus here if minus infinity plus infinity if you add. So, it is going to be from 1 to 1 and minus 1 if I add. So, what I have is minus L by 2 to L by 2. So, you have f of t e power n is from, n is 1 and n is minus 1. So, you have a 2 times, you have a cos, instead of this thing you have cos n omega naught x minus t dt. So, this is what you have because of rearrangement and then addition of those two, each addition of minus k and plus k terms if you do, this is what you get, okay. So, that you have this nice form. This is possible, first of all this step is possible because of uniform convergence. We are not proving the convergence of the Fourier series here. If it converges, it has to go to only a function, not anything else. So, if I pull this together, so again I am trying to pull this integral out of this series, that is also possible because of uniform convergence. If I do this, you see there is going to be minus L by 2 to L by 2 f of t, if I write it 1 by L plus 2 by L sigma n is from 1 to infinity cos n omega naught x minus t dt. So, this is the series to dt. Again this step is also because of uniform convergence, you have this. So, let me call this as some new function. So, let d capital D of x minus t as 1 by L plus 2 by L sigma n is from 1 to infinity cos n omega naught x minus t. Let me represent like this. Now, in this here I take the digression, digress a bit to define what is a delta function here. A delta function is not a function. So, delta function, so first of all usual functions which you have continuous functions, differentiable function, which you all these usual functions which you see, they are functions that are defined, it does not take any infinite value, okay. So, any the generalized functions are a limit of usual functions, okay. So, first of all if I define what is generalized function, generalized function if I define as a limit of usual functions, limit of usual functions in an average sense. In an average sense is called a generalized function. Limit of usual functions in an average sense is called a generalized function. For example, I will just give you So, I choose the delta function itself. Let me choose this as my first function 0 here, suddenly there is a jump, there is a 0 again here from here to here. Okay. So, this is 1 again, next this is your f1, f2 is 0 up to here, go up and you go up and again 0, and this is your f2. Like this you go on getting it like this. Okay. 0 if it's 1 here, 2 here, 3 here and so on. Okay. And this is if you go on as n goes to infinity, as like that you go on, you have fn. Fn if you consider for any each n, this is a usual function, because 0 at some place it is a finite number and other places it is 0. Okay. This is a usual function, but you consider the limit as n goes to infinity, what you get is 0 for every value x is not equal to 0. Okay. Because eventually it is this 0, this around 0, both your eventually 0. At 0 you are getting, as you see, there is a 3 n is value is n at 0, at some small neighborhood of 0 is n. So, at x equal to 0 it is infinity. So, such a function, so this is not a function, what you get is the result of this usual function, but this is called the generalized function, and it is a limit. So, what do you mean by this limit? This converges to this function. This is some average sense you have to look at it, that is fx, you consider some gx, take the average wherever this integral makes sense. Now, you look at this n goes to infinity, this average minus infinity infinity, so that this integral makes sense. You consider all gx such that this integral makes sense. This is equal to, if I call this as some new function, let us say generalized function capital G of x. So, what you have is g of x into your any test function, if I call this g any gx, that makes sense. Okay. So, this converges to the finite quantity like this. So, this is this limit converges on an average fn converges to gx, that is the meaning of this. So, this is a weak convergence. Okay. On an average means a weak convergence. So, that means fn of x converges weakly on an average to g of x, that is the meaning. Okay. So, that is what happens for certain limit of functions such as this. So, delta function is one such thing. So, delta function is a generalized function. So, how do I define this delta function? As delta of x, which is 0 at x equal to 0, at x equal to x not equal to 0, infinity at x equal to 0. So, this I can represent this as a limit of some usual functions fn of x as n goes to infinity, where fn of x I define as I can define this as how do I define? You can yourself construct, if you take this minus 1 by n to 1 by n, for example. Okay. So, if x is between minus 1 by n to 1 by n, this is value is its value is n, for example. So, what is the difference? This integral value is, and so I define like this, n outside, otherwise 0, otherwise 0. For example, let me put it, it is not. So, what happens? What happens for each n I maintain and integral value of minus infinity to infinity fn of x dx. If you take the integral value, that I maintain as a constant. Okay. So, such a limit of functions is called delta function. So, delta function not only this is a limit of usual functions, but you also maintain this area. For example, this integral value has to be 1. So, if I choose this here fn of x n times minus 1 by n to 1 by n dx. So, this is n times what is the value of this 1. So, that is 1 by n minus plus 1 by n. So, you have 2 by n. So, you have 2 by n. So, in order to get as 1, so this should be n by 2. So, I define this as n by 2. If I define n by 2, so this will be simply 1. Value is maintained for every n. Okay. So, because of this you have this property is true. Okay. So, you have many representations for such delta function. So, you can have different fn values, different fn's, different sequences converges to this property, converges to this type of function, and also keeping the average value is 1, integral value is equal to 1. Such a function is delta function that plays an important role in the physical and engineering sciences. For example, when you consider instantaneous loads in the civil engineering, so you use these delta functions. Okay. There are many other places you can use this delta function. So, we also make use of this, we also use this delta function. You can also apply Fourier transform, you can also do Fourier transforms on these delta functions in our course. So, these are also useful. You can also apply Laplace transform on this delta function. So, once you have this delta function, so I will try to prove here that one of the property of the delta function is once you have such a delta function, what you have is average value of this fn of x. If you multiply any f of x, or rather a delta of x, if you multiply with fx, its value equal to dx equal to f of 0. So, how do I prove this? This is the property of delta function. So, this proof you can easily see as minus infinity infinity. Delta, you have seen that is the usual limiting value of this is actually, you can write it as limiting as n goes to infinity fn of x fx dx. Okay. So, LHS is this. So, this you can write it as a limit n goes to infinity. So, this is from minus 1 by n to 1 by n, and you have fn of x is n by 2 and fx dx. Okay. So, this is n by 2, that is a constant comes out, limit n goes to infinity. This is from minus 1 by n to 1 by n fx dx. So, by calculus you can have this average value, you can consider n by 2 as 2 by n times f at some value. So, you have if f is a usual function. So, f is this here multiplication function that we have for any usual function f x, okay, for any continuous function, let us say continuous function or differentiable function, okay, f x. So, if I choose such a f x, you have this theorem in your calculus f x dx. This value actually b minus a times f of c. C is, if f is continuous, c is the value between a and b, okay, for some c like that. So, you can write like here. So, you can have some c where c is between minus 1 by n to 1 by n. So, if you have this, now you have the limit. So, you still have the limit. So, you cannot write outside. So, this is the limit. Okay. So, this limit, once you have this limit n goes to infinity. So, this n goes. So, what you have is this limit n goes to infinity f of c. C as n goes to infinity, this becomes minus 1 by n to 1 by n. You end up getting as n goes to infinity, this is nothing but f of 0. So, this is the property that we have. This is your right hand side. So, with this preamble on this delta function, we can make use of this delta function here. So, what we have is this Fourier series that we have Sx is actually f of t times this. If I show that this d of x of t is a delta function, it behaves like if this is actually kind of a delta function, then I can show that this value is equal to fx. Okay. So, that is what we will see. So, one immediate thing which we have is, if I have instead of 0, if my instantaneous load is my concentration is only at 0, okay, this is how you are putting your concentration, limit of sequences. So, what is the delta function of x minus t is a concentration as a function, as the limit of fn of x minus t as a concentration at some value t. Okay. So, you can have such a thing. Then you have some immediate corollary of this property is integral delta of x minus t into f of t f of x dx as minus infinity infinity is actually equal to f at t, okay, for continuous f of x, continuous function for any continuous function f x. So, this is what exactly we use there. Your Fourier series, what we have is 1 by what we get is minus L by 2 to L by 2 f of t. So, what we have is d of x minus t. If I show that this is actually kind of delta function, we have dt, this becomes f of x if f is continuous. Okay. So, that is exactly what we are going to show. You can also use make use of the delta functions if it is a discontinuous points. If it is a discontinuous function is discontinuous, you can also write this as you can have one more property that if you use 0 to infinity delta x f x dx. This will give you, because of your concentration only, you are only looking at the positive side. So, you have only this part, if you look at it, half of its contribution will be half. So, you have half of f of 0. So, if I do like this, if f is discontinuous points, you can use this if f is continuous, this one, otherwise f x plus f x minus divided by 2, half of f x plus for f x plus to infinity, other part is minus infinity to f x minus part. Up to here you will have half contribution here, half contribution here, because of this property. So, only thing I have to show is d of x minus t is actually delta of x minus t. So, how do I show this? So, to do this, let d of x minus t, as I put it as a limit x goes to, so I introduce some new parameter here as dr of x minus t. So, where d of r x minus t is, you have this series L by r 2 by L times 1 by 2 plus, this is actually 1 by L, I am writing like 2 by L times 1 by L. So, that I can take this series 2 by L out in this series, n is from 1 to infinity. So, instead of simply cosines that we have for d of x t, you introduce r power n times cos n omega naught x minus t dt, x minus t. So, this is what you have. So, by introducing this, as r is less than 1, what you have is this modulus of this this inner in this sum is always less than 1. If mod r less than 1, then what you have is mod r power n cos n omega naught x minus t is also less than 1. So, because of this I can sum, because this becomes a geometric sum. So, I can sum it up easily. So, for that reason, only for r less than 1, mod r less than 1, this is this makes sense, this is finite. So, as r goes to 1 minus, because less than one side you approach the limit, that you define it as d of x of t. So, if you allow r goes to limit of r goes to 1 minus, this is actually d of x minus t, that you can easily see, put r equal to 1, that is exactly what you have, that is your d of x t. So, by defining like this your d, and then you can write you can sum it up, this you can add it, and you can write this as limit r goes to 1 minus, and you have a real part of 2 by L times 1 by 2 plus sigma n is from 1 to infinity r power n. So, I write simply, instead of cosine I write exponential function, so that I write real part of it, e power I n omega naught x minus t. Okay. So, remember omega naught is 2 pi by L here. So, this now if you can add this 1 by 2, so this becomes, so if you add this series I can add, and you can easily see that 2 by L that is our dr, okay, dr of x minus t. If you add this series, you see that 2 by L. So, if you add this, what you see is real part of 2 by L times, this becomes 1 minus r square plus I 2 r sin x minus t omega naught divided by 2 times 1 plus r square minus 2 r cos omega naught x minus t. You can write here as sin omega naught x minus t as to one term for sin. Similarly, for cos, this omega naught as put it as one term. So, this is what you can easily see by adding this as a geometric series, that is like sigma r power n, n is from 1 to infinity, is actually r power 1 is r. So, r divided by 1 minus this geometric thing is, that is r, okay, something like this. Or you have n is from 0 to infinity, r power n is simply first term is 1 minus r. Okay. This is, if I use the sum, you can easily see that this is the result. Okay. So, this if you take the real part, if you nicely see, so 2 goes, so you end up getting 1 by L 1 minus r square by 1 plus r square minus 2r cos omega naught x minus t. Okay. Now, what you do is you know that d of x t x minus t is a limit of dr of x minus t as r goes to minus 1 minus. So, you take this limit r goes to 1 minus. So, if r equal to 1, you can easily say if x equal to, so this is, you can easily see if x is not equal to t, this cosine function never be 1. If x is not equal to t, cos omega naught cos 2 pi by L times x minus t, as long as this is not equal to 0, this never be 1 if x is not equal to t. So, for that reason this numerator, this denominator will never be 0, and what you get is numerator is, but numerator is going to be 0. So, you have 0 here. Otherwise, what you have is if it is 1, if x equal to t, you have this becomes 1 and you have this becomes 1 minus r whole square, numerator is 1 minus r square. So, you have this is nothing but 1 plus r divided by 1 minus r. So, as r goes to 1 minus, is actually going to be infinity. So, this is exactly like your delta function. You cannot still say unless you show that integral other property of the delta function, integral value of delta and integral value of d of x minus t dx minus infinity infinity. So, you have to show that this value is equal to 1. If I just multiply with any function 1, and if any continuous function, if you multiply, it has to become f that function value at t. So, here I choose this as 1. So, if I choose this, this is sufficient. So, if I choose this, if equal to 1, then d of x t x minus t is actually delta function, actual delta function. Okay. Here still here I cannot say, though it's taking 0 at x equal to t, x is not equal to t, at x equal to t it's taking infinity, it looks like delta function, but if I provide only this, then you clearly say that d is actually delta function. So, how do I see this? Again because we know that this is dr is d of x minus t dt dx is actually a limit of r goes to 1 minus. Okay. So, this is minus infinity infinity, and this is your dr of x minus t. Because of the uniform convergence of this dr of x minus t, which is a series, and I am just putting r, I can bring this integral inside, and you end up getting this limit you can take it inside. Okay. So, I can exchange these limits and you have this dx. So, if I show that this value is equal to fixed, if it is equal to 1, that is, then I am done. So, to show this is equal to let me look at only this one. Okay. To show this this is equal to to show that this is equal to 1, let me choose this dr of x minus t dx. This if you calculate minus infinity infinity. See, as you see dr of x minus t outside, because it's coming from the Fourier series. So, outside you can assume that it is 0. Okay. dr of x minus t or d of x minus t between x minus t is if x minus t is between minus L by 2 to L by 2 only, this is true. This is outside, you can safely assume that is 0. Okay. Just like you have a periodic signal which is only periodic between minus L by 2 to L by 2, outside you can take it as 0. So, if I do this minus L by 2 to L by 2, this will become minus L by 2 to L by 2, the dr of x minus 2 is 1 minus r square by L times 1 over 1 plus r square whole square 1 plus r square minus 2 r cos omega naught, that is 2 pi by L x minus t dx. Okay. So, this is equal to, so you can easily show that this quantity is equal to 1. How do I show this? This is equal to, so you can take this out, 1 minus r square by L minus L by 2 to L by 2, and here before I do this, so I will write x minus t as x dash, so that you have dx is dx dash divided by 1 plus r square minus 2 r cos 2 pi by L times x minus t as x dash, and this becomes, when you put x equal to minus L by 2 to minus t, this minus t because of this periodicity, and I can simply, this is again same as minus L by 2 to L by 2, okay, because dr of x minus t is 0 outside. So, it is anyway periodic, so it does not matter. So, it's, you can this is cosine function is periodic, so you can have this. This is same as this. Okay. So, this is actually minus t and minus t because of this cosine function which is periodic. So, that is actually same as this one. You have 2 pi by L. So, you have, that is why, that is the reason. Okay. So, x is a dummy variable, I can remove these dashes. So, this is what you have, and the next step is let us choose 2 pi by L x as t. So, if I do this, you have 1 minus r square by L, this becomes when I put this becomes minus pi to pi, dx is L by 2 pi times dt 1 plus r square minus 2 r cos t. So, L goes, and you have this 1 minus r square by 2 pi. So, again this is a even function, integrand is even function. So, you have 2 times 0 to pi dt by 1 plus r square minus 2 r cos t. So, 2 goes here. So, you end up simply pi. So, again this one I can split this into 1 by pi part pi by 2 and pi by 2 to pi dt by 1 plus r square minus 2 r cos t. So, again if I choose in this integral, if I choose t as x minus pi by 2, and we get our x equal to t minus pi by 2, at t equal to pi by 2, so it becomes 0, and t equal to pi, it is pi by 2. So, and this bar, but cos t becomes minus cos x. Okay. So, if I use this change of variable in the second integral, so you end up getting 1 minus r square by pi times, so you see that this is going to be 0 to pi by 2. So, if you add this, you get 1 plus r square whole square minus 4 r square cos square t dt. What you have is 1 plus 2 into 1 plus r square times dt. So, you have 1 minus r square 1 plus r square into 2 by pi times integral 0 to pi by 2 dt by, and here one more step I do is I write cos square t as 1 by secant square t. So, if I put this as 1 plus r square whole square 1 secant square, that I write it as 1 plus tan square x tan square t minus 4 r square, so that you can take this secant square t dt. Okay. So, this is what you have. Now, put tan t as x in this. So, you end up getting 1 minus r square 1 plus r square 2 by pi times here 0 to pi by 2. So, if I do this, t equal to 0, tan 0 is 0, t equal to pi by 2, tan t, that is x becomes infinity. So, you have dx 1 plus r square whole square minus 4 r square plus 1 plus r square whole square times tan square t, that is x square. This is what you have. So, this if you pull it 1 minus r square 1 plus r square 2 by pi. If I pull this part outside, what you get is this is actually equal to 1 minus r square whole square. Okay. So, this if I pull it apart, and you have a 0 to infinity dx divided by 1 plus r square by 1 minus r square whole square x square. So, this gets cancelled here. So, you end up getting 2 by pi times 1 plus r square by 1 minus r square integral 0 to infinity dx by 1 plus r square by 1 minus r square x whole square. So, this is actually equal to 2 by pi times tan inverse 1 plus r square by 1 minus r square x. This you apply 0 to infinity limits. This is at infinity, this is pi by 2, at 0 this is 0. So, you have 2 by pi times pi by 2 minus 0. So, this is actually equal to 1. So, this is what we have shown. So, this implies the dr. So, this means when you come back here and write it here. So, this integral value have shown that for any irrespective of value of r, this limit r goes to 1 minus is actually constant. So, this is actually equal to 1. So, delta function is this and delta function integral value is 1. So, this implies d of x minus t is actually delta function. So, that means what we have is this Fourier series. If you come back and use here, this is actually if you use the property of the delta function, this is minus L by 2 to L by 2 f of t. Now, you have this in the place of this you have a delta function delta of x minus t dt. So, this is nothing but f of x if it is continuous. Okay. Otherwise, because again using the delta function property, if it is a discontinuous, you can have if f is discontinuous at x plus and x minus both the places you have a jump. Such a jump you have if it is a discontinuous jump here to here. Okay. So, minus infinity to here 1 and here to infinity 1 if you consider. So, each contribution by the delta is half f x plus half at half x minus. So, this is exactly what we have if at discontinuous point. Discontinuous point, continuous point. At continuous point, this is what is the case. Okay. So, that is what we have seen that if it is a continuous function, this Fourier series need not converge, and if it converges, actually we strongly assume that it is uniformly convergent. Fourier series actually converges to f x. In the process, we have defined what is a generalized function. On such example is the delta function. We made use of this delta function to show that the series actually converges to f x and its average jump value. Okay. So, with this we will do more examples in the next video for the convergence of the Fourier series. When you consider such examples, usually they are in terms of elementary functions, they are piecewise smooth. So, that a Fourier series convergence is guaranteed. Okay. Thank you very much.